and then has a contour, goes along the imaginary time axis, that has a contour that comes out in real time and comes back in real time. Such a path integral, which is half imaginary time, half real time, has been used by many people, Schwinger and Keldysh in particular, the names people usually quote. And these path integrals can now be used to probe not just equilibrium properties in thermal physics, but real-time properties of thermal physics. Because you can then, along these real-time paths, put insertions that tell you about real-time correlators of, let's say, the stress tensor. So very natural generalization of the question of the partition function is to compute this partition function, the partition function in thermal equilibrium, plus this excursion into real time, as a function not just of the metric on this contour, but the metrics on these contours. If you can compute all these partition functions, you will have in principle computed every possible correlator of the stress tensor that you could want to imagine, that you can write down. So we will have a lot of information. Okay, now this is a much tougher problem than writing down the partition function. It is much tougher because, unlike the partition functions, this path integral is not a local function of the metrics on these two contours. The reason for that is simple. As we've seen, hydrodynamics has light bones. So one of these insertions hits the real-time degrees of freedom of the problem. That's hydrodynamics. That propagates, causes a response somewhere else. Very non-local. This is a mass response. Okay? So the problem of the partition function itself is not a very, is not what you want to ask. Because usually in physics you don't get anything useful unless you use local things. Okay? What you really want to ask is for a local structure that will reproduce the partition function. So the question that you might ask is there a local effective action along this contour that you can write down such that when you solve the equation of motion of this local effective action, or you do the path integral with this local effective action, you reproduce this non-local partition function. Okay? Now, this problem is still in progress. It's not been 100% solved, and I have not played any role in this. But just by reading the papers, it looks like there's been a good deal of recent progress for this book. Two groups, Loganayam and Rangamani on one end, and Hongliu and collaborators on the other, have looked at the problem in slightly different ways and got sort of similar answers. Both of them write down an effective action whose fields are interesting. The fields are diffeomorphisms on the four-dimensional boundary manifold. Okay? And then they write down some action with these diffeomorphism fields, demand that this action have a lot of symmetry, including some sort of BRST symmetry and various other things. And in the end, claim to get many of the structures, perhaps all of the structures of hydrodynamics out of their analysis. Okay. So these guys claim, I'm not 100% sure myself if it's all kosher yet, but they claim to have some sort of action. I think they're very near finding that they haven't found it yet. They claim to have some sort of action which will produce all these real-time thermal correlators for you. Now I find this very interesting because this action in principle should determine all of the long-distance dynamics of your system, including fluctuations. Okay? So this action should produce the dissipation of hydrodynamics classically and the fluctuations of hydrodynamics quantum mechanics. The same action, just path integral of the same action, produces both dissipation and fluctuations. I think this would be, getting this straight and making it useful would be very interesting. By the way, there's an interesting open problem here, which is try to recover this structure through gravity. All of the progress that I've told you about so far got great impetus from the fact that we could produce fluid dynamics from gravity. Because you see, arguments like what else can it be sometimes go wrong, because somebody eventually shows you what else it can be. Okay? These kind of symmetric type arguments, human beings in my opinion are not that good at. Okay? It's good to be guided by an example. I think here, all of this has been constructed by what else can it be. I think it would be very useful to have one example. Perhaps somebody could work out the gravity problem for this action. I think that would be very useful. Okay, the last thing I'm going to say in the next 2 slides and then stop, is to flag another recent development, in fact the development on which I've given my lectures at the school. which is the relationship between gravity and hydrodynamics in another context, other than the one that I told you about. So far, I've been studying gravity at long wavelengths in asymptotically anti-de Sitter space. Now, asymptotically anti-de Sitter space is very natural for a string theorist to study because of the gauge-gravity correspondence, but doesn't seem like the simplest gravity theory to study from the point of view of gravitation. The gravitational physicist would plumb first for flat space. So you could ask, is there any sense in which the dynamics of horizons of ordinary black holes in flat space is governed by the equations of hydrodynamics, much like the equations of the dynamics of black brains in ADS space was governed by the equations of hydrodynamics? That would be very interesting, not least because it could make contact with people who are interested in experiments involving the dynamics of black holes in 4 dimensions, like LIGO. Okay, now, at first sight, when you ask this question, first you think about it for 2 minutes and you say, of course the answer has to be no. Why? The answer has to be no because, you see, everything that became simple happened because you had a parameter. The parameter was the long wavelength expansion. Okay? Now, suppose you've got a black hole in flat space. Let's say its radius is r0. Okay? There's no scale in the problem other than r0. Gravity in flat space has no scale. Okay? So you've got r0. Now, the only way that you expect simplicity is if the distance is much larger than r0. But that makes no sense because everything's happening on a sphere of size r0. So how can it be larger than r0 on a sphere of size r0? Sounds like the problem makes no sense. And in 4 dimensions, or in a fixed number of dimensions, that would be correct. The problem makes no sense. However, there's an interesting observation. The interesting observation is this, that if you vary the number of space-time dimensions, then it turns out dynamically the black hole develops a second scale. I don't have the time to tell you the details of that, but the scale is roughly the thickness of the black hole. The distance from the event horizon you have to go before you can no longer see that there was a black hole. Just the fact that Newton's law dies off so fast in a large number of dimensions makes the distance small when d is large. In fact, that distance turns out to be r0 divided by t. And it turns out that there is a useful long wavelength expansion you can develop on length scales large, not compared to r0, but compared to r0 by d. As we've seen, the largest wavelength in the problem on a sphere of size r0 is r0. So the only way it can be large compared to r0 by d, but not larger than r0, is if d is very large. Okay? So, but in this limit, in the limit where the number of space-time dimensions are very large, you can develop a useful expansion of black hole dynamics. Just like in the case of the ADS black holes, where we showed that the effective theory of gravity in this long wavelength limit was a set of non-gravitational equations, which is fluid dynamics in a flat pattern. Once again here you recover a set of non-gravitational equations. But these non-gravitational equations are gravitational equations are sort of interesting. The variables of these equations are the shape of a sort of membrane, a codimension 1 membrane, you think of it like soap bubble, and the velocity field on this membrane. The equation of motion of this problem are the conservation of a stress tensor that is localized on this membrane. So, as dynamics proceeds, the shape of this membrane flops around, the velocity fields move around according to equations of basically hydrodynamics. And this problem of soap bubble type hydrodynamics is due to black hole motion in a large number of dimensions. It sounds like a very cute observation to me. It hasn't yet had concrete impact, partly because concrete impact in the sense that it hasn't yet discovered new terms in the equation of soap bubble hydrodynamics, since in order to have new terms, you need to have old terms. Nobody seems to have looked at this problem very carefully before. But the structure looks very interesting to me. It's a new game. What it will do, I don't know, but it looks interesting. It's a second context in which you've got hydrodynamics to do with the gravitational dynamics. Okay, that's it. Let's review what we found. We found asymptotically ADS d+1 gravity reduces the long wavelength limit to the equations of d+1 dimensional Navier-Stokes equations with gravitationally determined dissipative parameters, constitutive relations. Similarly, flat space horizon dynamics maps to the soap bubble hydrodynamics at large scale. The results from the implementation of the ADS part of this program has corrected errors and widely accepted results of the general structure of the equations of charge relativistic hydrodynamics and superfluid hydrodynamics. Didn't have the time to tell you the superfluids. This is a whole other story. Many new insights into the structure of the equation of hydrodynamics follow from this stuff. There's effective understanding of the second law within hydrodynamics. Progress towards developing an action formalism for thermal dissipation and fluctuations, which I personally find very interesting. The gravity duals of these statements are still to be developed. There's a recent generalization of the fluid gravity correspondence to horizon dynamics in flat space and large D. These equations of sort of the dynamic. We'll look at the dynamics of a sort of soap bubble with a fluid living on this soap bubble. The degrees of freedom are its shape and velocity. What is this good for? I will get it. Okay. That's it.
The addition of the hydrodynamics that you found, can I think about it as all this stuff?
Oh, all this stuff. Well, you'll have to tell me. I'll tell you what terms it is. People know. It's nonsense. But it is in a three. It's in a 3 plus 1 dimensional field, not 2 plus 1. Yes. Yes.
Maybe it's just a way to do the calculation.
Yeah. The comment is the large D looks unphysical, and I agree with that. It looks unphysical from 2 points of view. You see, as far as we can tell, we don't have a single example of quantum gravity in an arbitrary gravity. Yeah, so this makes quantum gravity in a large number of dimensions a tricky game. I mean, a risky game, because you may be studying a theory with no examples. Okay? However, of course, classical gravity is completely verified. Now, the point of view I take is that in the study of classical gravity, it's just a parameter that allows you to study things. And eventually, you may be interested in D equals 4 and D equals 10. But you try to understand things by introducing a parameter to it. Exactly, like large area interstellar case. Exactly.
So presumably you get different constitutive relations if you start with a theory of gravity with different terms in it.
Yes.
Is there a one-to-one correspondence between like effective theories of gravity and possible constitutive relations?
Yeah, that's a very interesting question. I'm not sure if it's one-to-one. You see, because the infinities are different. It doesn't sound like one. You see, because it may be one-to-one if you go to all orders in the derivative expansion. See, there are 2 different derivative expansions. There's an alpha prime expansion that you can imagine on the bulk side. And there's a boundary derivative expansion on the boundary side. And these are totally distinct. Okay? You can work to leading order in the boundary derivative expansion and to all orders in the alpha prime expansion. Now, to leading orders in the boundary derivative expansion, there's only one term, namely the viscosity, where there's an infinite number of functions. Maybe if you go to all orders this way and all orders that way, there is some complicated one-to-one, where it's not clear. Now, the question is very interesting for the following reason. Well, for many reasons, but the issue of entropy increase in hydrodynamics, as I tried to indicate in this document, I mean, it says sufficiently, is completely clear. Shantanu Bhattacharya has completely solved the problem of parameterizing the most general entropy current that is always positive divergence. Okay? Now, this problem in 2-directed Einstein gravity mapped to the problem of area increase. In general gravity, it should map to the problem of wall entropy, which is an open problem of gravity. Okay? So it would be nice to understand this. By the way, for that question, large D might be the more direct way of getting it. Again, I don't have to tell you all that, but on this large D membrane, we've got an entropy current, which is also positive divergence. Somehow that feels like better expansion to me than working in ADS, because the large D membrane is very closely tied to the actual divergence.
Hey, any last questions? You seem to indicate at some point that you have a BLST symmetry. What is the physical source in this case?
I'll tell you what the physical reason is. Okay, you see, I should say this is not my own work, and I hope I'm not misrepresenting it, but let me say it anyway. You see, what what you're doing here is to write down an action for dissipative stuff. So the paradigmatic dissipative equation is a damped harmonic oscillator. Suppose I want to write down an action that produced a damped harmonic oscillator. At first sight, you might think all I have to do is to write x double dot plus x dot into x, and you've got an action. But at second thought, you see that's wrong. Because the x times x dot is a total derivative. It's d by dt of x squared. Okay? So that doesn't work. It doesn't work for a reason. It shouldn't be too easy to produce dissipation from an action. Now what you can do is to take x double dot plus x dot times y, a second field. This is not wrong. You vary with respect to y, you get the dissipative equation for x. But there's a problem. The problem is now you vary with respect to x. And you get an equation of motion for y, and it's an anti-dissipative equation. This had to be, you can't respect Liouville's theorem of conservation of volume and space with dissipation, unless dissipation is accompanied by anti-dissipation. So, the general structure of these actions is always this way. You introduce a dissipative mode and an anti-dissipative. But you want to make sure that the anti-dissipative mode for appropriate physical questions is unphysical, is killed. And you try to do that by making it PRST. That's roughly the physics. From there to the formulas, I'm not sure I could take you.
Negative norm states will be.
Yes, you make sure they equal. That's the idea. That there's some junk, but we'll keep it junk. We won't let it pollute our physical system. Yeah.
In 5 dimensions and higher, there's a Gregory-Laflamme instability,
Yes.
which persists up to arbitrarily large dimensions,
Yes.
presumably.
Yes.
And this formalism allows you to localize the horizon, so perhaps can answer the question about the snapping. Has this analysis been done?
Okay. Yes, it has been done. It was done first by Francis Tanabe, and we repeated it with our formalism. Unfortunately, there's something else. Okay. The Gregory-Laflamme phenomenon changes its nature in 13.5 dimensions. Have you heard of this? Okay. You see, when you have a black string, and it has an instability, it always has an instability. Okay? Now you could ask, where does that instability go? If you're in less than 13.5 dimensions, the instability goes to snapping, to black holes. In higher than 13.5 dimensions, it goes to a weakly black string. Yes, this was known before. So the Large analysis unfortunately expands around d equals infinity, so it takes you to the weakly black string. And you can completely follow that process. You can follow the time-dependent evolution to the process. Okay? But it's not the really interesting one. Yes, please.
Okay, so we're a little bit short on time. Shiraz is going to be here for a week, so you can ask him questions later.